Hey, future engineers, welcome back to part two of our CFD series. Last time we simulated subsonic airflow over an ACA 2412 airfoil, but today we'll be simulating supersonic airflow over an everyday object that you see at home. What I'm going to be using is actually the 64-ounce Hydroflask Growler that I have just laying around at home. And I actually simulated it in SolidWorks to make it a 3D model. Rather than simulating, I actually modeled it and it is up to scale. I got the dimensions from the official website from Hydroflask and converted them into meters to make it both compatible in not only SolidWorks but also in Cradle. So, with that being said, this one's less about lift and more about the wake formation, the drag, and flow separation. And we're going to see how a blunt everyday object like our tumbler here behaves when it hits air at over Mach 1 or supersonic. So if you're curious about how air flows around common objects in extreme condition works, stick around. Okay, so to begin our simulation for our hydro flask, let's begin once again by launching our preprocessor in scFlow. So that will be once again here. This first icon right here. Just simply click on it and let it load. Okay, and wait for it. And as we wait for this to load, there we go. I'm gonna go ahead and well tell you that unlike the last video, our part one, I won't be explaining much in terms of detail since we did cover it with the first video to make this tutorial a bit shorter in comparison to our first video. So we're going to be going down to just the bare steps in this video rather than me explaining everything over before clicking and continuing the process. Okay? So now that we are in scFlow preprocessor, let's name our project. This will be, last time I named it NACA 2412 airfoil. As I can see here, I'm gonna go ahead and name this one Hydroflask. Mm, object underscore simulation or sim. Okay, great. And also, you know the drill. My cursor is surrounded by a red opaque circle to make it easier to track my movements as we go through this process. And same as before, I'm gonna go ahead and remove my camera so that you see the full screen for scFlow preprocessor. Okay, so now that I am no longer in the screen and you can see the full view of scFlow preprocessor, we can begin our uh, our tutorial by importing that growler that I just mentioned. You see here, documents, AirLab 2, and as you can see, it's here. By the way, just a quick sneak peek of the object or a full view of the object just to give it some uh, time in the spotlight. I'm gonna go ahead and show to you how it looks like. There you go. And there is a fun part here. If we look closer to our hydro flask, if you can notice, there are these spaces or gaps. Since in reality, this right here, this would actually be the cap itself. And this is just a part of the handle. And this would be the metal accent that we have on our hydro flask. Okay, give me one quick second. I'm gonna turn the camera back on so I can show you in real life or through the camera. Okay, so now that my camera is back on, here is the hydro flask in reality. So this is what I was talking about. This actually screws off as this is going to be the cap itself. And this right here is the stainless steel that we can see here. Give me one quick second to zoom in. There we go. So yeah, that's going to be this part right here, but with the cap screwed on. Okay, so closer look. That should how it looks. And not only that part has a groove, this part also has a groove right here. See this part right here, it also has a groove. So that should make some interesting points when simulating the airflow in cradle, since air does pass through those gaps. Okay. Okay. So going back to cradle, that's the kicker. 1%. There we go. That should be cradle right there. I'm gonna go ahead and import my IGS file. So last time we used the NACA 2412 IGS. Now I'm gonna be using the Hydroflask underscore growler underscore 64 ounce dot IGS. Opening that up, it should extracting it and translating it in Cradle. There we go. Now that we can see our tumbler here or hydro flask fully modeled. There we go. That's what we're going to be subjecting to supersonic flow. So uh, to continue our process here, same as before, we're going to go ahead and create a cuboid, which would serve as our fluid domain. So in order to do that, we must first select our hydroplask here. So here's a new trick that you could use rather than clicking it. If you have multiple pieces, go ahead and just click select part surface, just like that. Calculate size, same as before, and extend surroundings. So as the size of my tumbler here is 11.4 inches in reality, scaled down to for our SolidWorks 3D model here, it shows the size of 0.12. And I believe that should be the conversion of inches to meters. Okay. So the sides here, of course, before we use the 1 by 1 cuboid, now since the item or the object that we're simulating is smaller, I'm going to go ahead and put this in as 0.5. That should be the minimum side, maximum side as well. Okay. Once again, please Uh, take note that you should always tick this as register as fluid region. Okay, so before we do proceed, let's go ahead and take a quick look as to what the cuboid would look like. There you go. Since we selected the hydro flask, it is now the center of our fluid domain. Okay, now that's out of the way, we're gonna continue onwards to giving our cuboid the material of it being an incompressible air. Once again, this should be blank before moving forward. Make sure that this is blank and does not say obstacle. Okay, now we're gonna go ahead and click on fluid, since by default it will show you solid attributes. So click on fluid and drop down that gas incompressible to give you the option of air incompressible. Simply click apply to make sure that it does uh but it does give that attribute and material to the cuboid. Okay, and that we see that it is highlighted as blue. Click OK, and that should now show us that the material is now air incompressible for our cuboid. Okay, next. Moving forward, after preparing our parts here, we can now check if there are anything else that we need to do. And once again, if you have a specific setting for your mesher or faceter, the mesher slash faceter setting is there for you to configure. Okay, since I don't have anything that needs to be tweaked, I'll just simply click OK and move forward building my analysis model. So once again, that would be the build analysis model, a part here within our navigation tab. Okay, let it build that analysis model for us. There we go. Let's just let it load until it's 100% done. Okay, now everything is highlighted as this dark blue. There you go. We shall now continue moving down the navigation tab and register the regions. You'll just simply click on register region for you to begin. There you go. And last time in the airfoil video, or as we simulated that airfoil, what we did was actually go part by part from the part three. There you go, part three. We went down from region, we went to surface region, then down to numerical region. You can do that as well, but for this video, we're gonna make it quicker, and this should serve as practice as well for our future engineers. So the surface region here, the TAD surface region should show up. Same process as before. Look for the face of your cuboid, whether your object, since mine is a cylindrical object that is symmetrical as well, any face would do, but we'll continue with the format of our airfoil as before. My face number two, would be the front of my uh, cuboid, or or it will serve as my inlet. Okay, so the region name will now be inlet for our phase two. So if the inlet is at the phase two, therefore the outlet would be the phase five, same as with the airfoil video. Okay, so register. Now we have the inlet and the outlet. We should also register the walls. So as I've said before, what we're trying to do here is simulate as if we have our own wind tunnel that we're placing our object inside in. So let's rename that as walls. And of course, if we don't have any object inside our wind tunnel, there won't be anything to simulate. So use the same trick as before that I showed you. Simply click on your object, or right click on your object here, right click, and it should show you the option to select part surface. Now, the reason as to why I'm doing this is because, give me one quick second. Oh, sorry. Okay, so the reason as to why I'm doing this is because, as you saw earlier in SolidWorks here, I actually have gaps, which if I tried to click on Cradle, it actually makes it difficult and it won't let me easily click those. Okay, so using the trick that I just showed you, simply right click, select part surface, and it should now show you all the faces that is your object. So as to mine, it reaches up to phase 37 out of, well, 37, since it also considers the cuboid, the walls of the cuboid as a surface. So imagine clicking all of those parts one by one and being stuck, not being able to reach those gaps, same as mine. So simply using that trick helps you out. So I'm gonna name this as object, just to make it simple. There we go, object. It shows 32 faces for me. So that should be it. Next, after going to surface region, we're going to be moving forward the numerical region. On our last video, we clicked this after closing the surface region, but now I'm gonna go and show to you that it is under volume region, and this will be our target, the numerical region. So same as before, we're gonna create a new numerical region, and we're gonna name it same as before, num x for me, and name it as you wish in yours. So we're going to be creating this numerical region inside of our cuboid. So inside of cuboid, and this coordinates right here are going to be our hydroflask once more. So select the part surface, calculate from selected parts and faces. It should show you uh, the coordinates for our hydroflask, or for our object. So extend surrounding. Since I did use a zero point 0.5 minimum side and maximum side, I'm gonna go ahead and half that and put in 0.25. There we go. So quick preview of our numerical region is going to be half of our zero point 0.5 surrounding. I'm happy with that. I'm gonna go and click OK and close out of our numerical region. So that's, yeah, so that should be our uh registered region part of this video. So we're gonna move on to the conditions. Now, before you do proceed applying conditions, make sure that your regions are properly registered since those regions are going to be used in creating conditions, as I had mentioned in the first video, and as I'm also mentioning now. See, we can see here the inlet, the outlet, the walls, and our object. So, continuing, if everything is up to the steps that we have been doing, or you're up to the steps that we have been doing here following, let's now give conditions to our inlet, outlet walls for the condition section of this video. So continuing inlet, for our inlet, we're gonna give that the inflow condition. And since we're doing the supersonic simulation now, we're gonna change the normal velocity to 343.2, since that will be the supersonic speed that we'll be using to subject our hydroflask to. Okay, so set. And if we have an inlet, we should also have an outlet with the outflow condition. Nothing to change here. Just simply giving that condition is good enough. So next, we're going to be putting in our wall boundary condition, clicking on walls, wall shear stress condition. Same as before, no slip will be turned into free slip. Now, uh, quick reminder, since by default you'll be seeing this, no slip, do not consider static, and it doesn't give you the direct option to give more um it does not give you the direct option to change to free slip unless you click on it. Since if I click no slip here, that is when it will show me the drag down option to change it to free slip. Okay, hope that helps if you're having trouble finding free slip. So set that. And continuing, on our first video we exit the condition wizard to later on just open it up. Now, what we're gonna do is move on to the output setting here, and same as before, go to surface data. So if you're not following, simply click on it. There you go. Simply click on output setting, output field, of file, and surface data. Okay. And what we're looking for is the wall shear stress vector. Since it shows by default, do not output, simply change that by clicking and giving it the option to be an output. Okay, there you go. Now that everything here in the condition wizard has been set, simply click on finish. Okay, same pattern as before. After preparing our parts, we registered our regions and set our conditions. Now, we're gonna go ahead and move on to the octree parameter. If you would like to use the minimum size of your object, feel free to use this. But as for my project here, I'm gonna go ahead and just use by default the target number of elements of 100,000. So let's create that octree. There we go. It is now showing our octree parameter. And that should be it for the octree parameter. We're gonna be moving now towards the mesh parameter, which is what takes the longest to load since it will be creating a mesh for our object or the, well, yeah, for the object. So by default, I'll be using 0.2 as the thickness coefficient, and a number of layers should be 2 as well. If you would like to tweak this, I once again recommend that you watch educational YouTubers that go in depth with creating mesh for more accurate results. For those who would like to do this as a hobby or do this as um, another part of you being an engineer, another tool of you being an engineer, I highly recommend looking for those. Okay, so I'm gonna go and create this mesh, and I'll be back with you when this has been loaded. Okay, so now that the mesh has been generated here within our preprocessor for our model here, we can go ahead and simply continue our process. So now that everything here has been set up down from the, well, starting from preparing the parts down to the mesh parameter, what's left now is actually just simply executing this and moving on to the SC monitor. So same as before, click on execute, save files for analysis, save the mesh file, save the analysis condition file, save the project entirely and execute solver. Okay, you're going to be prompted by this GUI right here, and it's up to you if you would like for the solve when the solver is launched, scFlow preprocessor will be exited. All up to you, okay? So I'm gonna go ahead and click mine once more so it won't exit, and I'll just click on execute, and I'll see you inside yeah, SC monitor. Sorry about that. Okay, so now that we're inside SC monitor, we're gonna go ahead and let uh, the solver do its thing and run our simulation for us. So just let it do its thing, and it depends on your object how many cycles will be generated or will be calculated along with the time that it will take for it to calculate your simulation. So before we had a cycle of 50, and since I believe we're in supersonic and we have a smaller object, this is going to be taking a bit of time. So I can go ahead and fast forward this process right here as it simulates, and I'll get back with you in normal speed once it's done. Okay, so same as before, we're gonna go ahead and run down from our U velocity down to our specific turbulence dissipation rate. So, uh, to begin, our U velocity or our X direction, let me go ahead and click all of this. So, um, this will be our X direction, the U velocity, our green line, and well, green line here will be the V velocity or the Y direction, and the blue line here will be our W velocity, okay? So if you would like a bit more detail on what those mean, I highly recommend that you watch the first video where we actually simulated the airfoil. But as a brief information, the U is the symbol for our x-axis, as mentioned earlier. It's the velocity in the horizontal direction. The V, or the green line right here, the y-axis, is going to be the vertical direction or the up and down motion. And the W here would be the z-axis, the velocity in the depth direction. It's the one that is out of or into the screen in a 3D model. Okay, so running down the list here, let me go ahead and bring those all back up. So in our early cycles, that would be the 1 to 20, right here, 1 to 20. The early cycles, as expected in supersonic flow, you see initial spikes right here, initial spikes. So mainly we're going to be talking about the turbulence energy, okay, along with the pressure later on. So for the turbulence energy, as we can see here, it spikes, it peaks above -2, indicating, well, it peaks below -2 on our case here, indicating dynamic development of turbulence and shock interaction, while the pressure drops quickly below -4. So it drops, it spikes, and drops once more. Okay, it drops quickly below -4 after early instability, therefore shock waves forming and stabilizing, as we can see here. Next, moving forward to in our cycles, the mid-cycle this time around, as we can see for the mid-cycle for the 20s to 80s, so from here to here, we can see that all variables begin to stabilize. So velocity components u, v, that's u, v, and w fluctuate mildly but settle around the negative 3.5, around here, to 4.0. So that will be around here. So from here to here, they fluctuate but settle around this area for the mid-cycle. Moving on to the pressure. So the pressure, as mentioned earlier in the early stages, it dropped quickly below -4. After instability, it spiked and, well, of course, it dropped. But for our mid-cycle here, it reaches below let me see, -6. So around here, it's beginning to reach -6 rather than it reaches below it. It's starting to reach -6, which is here, this line right here. And it's indicating a strong convergence in this variable. Okay. Next would be the specific dissipation rate. It steadily decreases, as you can see from our for our mid-cycle, it steadily decreases, and this is actually a sign of turbulence model stabilizing. Okay, so once again, this is a sign of turbulence model stabilizing. Next, moving forward from the mid-cycle, we're going to look at our late cycles. That's going to be the 80s to the 150s. So until it reaches 155. So most lines, as you can see here, and the trend is going to be downwards for most of the lines, showing continued convergence. Okay. Minor oscillation in velocity and turbulence energy are common in simulations with shock waves and wakes, especially for our body right here, the hydroflask, which is just, of course, a cylinder. It's symmetrical all the way around. And in my opinion, overall convergence looks good, especially for a supersonic compressible flow or incompressible flow. Okay, so uh, in conclusion, while not all the variables drop below -5, most are well below -4. See, right to the end here, most are well below -4. And key indicators are going to be the pressure and the turbulence dissipation, which are very stable. Okay, so if you ask me, this is a successful steady state result for a bluff body in supersonic conditions where minor residual oscillations are normal due to strong regions such as shocks and weak zones. So I believe that should be it for our hydro flask being subjected to uh, supersonic flow and its simulation under scFlow and scMonitor. So let me go ahead and get back with you with our main screen. There we go. So uh, I believe that should be the end of our video. And I believe I don't have anything else to cover in our tutorial right here. And same as before, if you would like other videos such as modeling the hydro flask or just a general uh, modeling video in SolidWorks, I'll be more than happy to do it for you. Okay? So, with all that being said, that's a wrap for our supersonic CFD experiment with our hydro flask right here. And you probably won't find one flying at Mach 1, but it's an awesome way to visualize high-speed aerodynamics. Until then, catch you next time. Keep flying, keep exploring. Goodbye, future engineers.